Recording is rolling. It is Friday, August 19th. Okay, so a lot of you guys are turning in the trigonometry page. So and a lot, most of you guys have actually turned it in by yesterday. So I will get that graded over the weekend. Uh, so yeah, next week we're getting into kinematic motion, which by AP's book, this is actually unit one. So everything we've been doing so far has been build up to this. Yeah, by about now the class is settling down. I know, first couple of weeks there's always students switching in and out. So yeah, I want to do stuff that's substantive and it's gonna help you guys out. But yeah, now we can actually really get rolling with class. Um, so Monday turns out it's going to be a weird schedule, but it's actually going to be really good for us. Right. So read my email and here's the news I got. Well, I think I told you guys this yesterday that your period one class, which is this class for you guys on Monday, is going to actually be 3 classes. Right. So the first 2 classes are all in this class. Right. And the news I have is that I'm not proctoring, so I'm going to be in here with you guys, and we're going to be doing the kinematic motion lab, which involves cars rolling down incline. Now, you might have noticed on Google Classroom, I did post a PDF or an Excel page, one or the other, of version of this lab. But since we have these new measuring tools, you guys remember the speed sensor, right? You directly measure speed, right? You guys remember that yesterday? Look at that, 1.67 meters per second. Oh yeah. Right, this is brand new. You guys will be the very first class that ever gets to use this. It's like a $60 piece of equipment right here. We have a whole set. Okay. I can go create a additions to that lab, and we can do new things that students have never done before. Then periods 2 and 3, you're not going to at all on Monday, and then everything's going to take up period 4. So you guys got to be ahead of my other classes. That'll be all right. Since you guys made AP class, we'll just do extra stuff, which would be perfectly good for you guys. So over this, yeah, now the schedule is going to be going. You guys are more regularly going to get college physics homework problems and quizzes are about to be coming up. So this would be like the last sort of slow weekend here, but you guys have lots of materials out there if you want to get a head start, look ahead a little bit. I have posted a bunch of kinematic motion assignments, but there are a bunch of textbook problems there. Your whole textbook PDF is up there. Do you guys remember AP Classroom? I think all but 1 or 2 of you by this point are on AP Classroom. So if you haven't gotten an AP Classroom yet, make sure you get there. And there's lots of resources already up. I posted a couple of progress checks that are not really assigned yet, but they're up there if you want to get a head start, look ahead. AP Daily videos. In fact, let me switch my screen over just so you can get your eyeballs on them, so something hopefully registers in your mind. But oh yeah, those videos are there. That's a good resource too. See my Zoom, share screen 2, and let's move over. Here it is, ready to go. Yeah. So unit 1 resources, right? It's what we're doing, kinematic motion. Okay, so if you want to get a head start there. Do I also have, I do also have up here classroom. In fact, I've got a specific tab up. Do I want to do this yet? It's gone here. Okay. So here's a bunch of stuff on Google Classroom, right, including all the class video recordings so far. And what are some things I want to point out to you guys? Paul Hewitt demos, these are pretty cool. I'll sprinkle some of these throughout the year. They're like 1-2 minute demos. Guys really get a personality and presentation style. So we got some of these pages that I've given to you guys. Oh, University of Colorado interactive demos. Those are pretty good. Physics posters, these ones hanging from my ceiling and ones I made throughout the entire last year. The college physics textbook. Those flashcards if you guys want those. Here's some of this recorded videos. Yeah, so lots of good resources there. There's AP Classroom. All right, so want to look ahead a little bit? There you go. But today, I'm going to do some dimensional analysis with you guys. Hopefully you guys have done some of this in chemistry, maybe, dimensional analysis. So here we go. This is a really powerful tool for, lots of reasons. We'll do some examples, so you guys will definitely get an idea. So remember how in physics, every single quantity that we work with is going to have an attached unit, right? Sometimes you can actually kind of figure out how things work, how variables might fit together possibly in an equation, or how things might be proportional to each other just by looking at the units. But let's do a couple examples, and then I have a short story for you guys. Okay, so question number one: how many days in 1 million seconds? Right, or it's equivalent to 1 million seconds. How many days would that be? I'm going to give you guys a little bit of time here. Get a head start. See if you guys can beat me to the answer. Oh, what is this? Yep. 11. That sounds about right. All right. So I'm going to do this this railroad track method. If you have a different way of going about this that you're comfortable with, then that's cool. But just for the notes, just one particular way. Okay. Does this look familiar, possibly from chemistry? Maybe depending on your chemistry teacher. Okay. So I'm going to start off with the given value, which is 1 million seconds. Oh, 1 million. Is that like 10 to the power of what? 6, 10 to the 6. Yeah. So you could write 10 to the 6, or if you want to write it in expanded form, it'll look like this. But don't forget that that number also has a unit. That's for seconds, right? And I'm going to use these railroad tracks as like a conversion. Okay. Now the question is how many days. So I want to go through some conversions and end up with like some number of days at the end of this, right? Maybe I can go. Hey, let's work out a plan. How about seconds to minutes, minutes to hours, and then hours to days? Going to do conversion. Okay. So the next one would be seconds to minutes. So, oh, well, there are 60 seconds in a minute. So see if you guys remember this. What should I do in 60 seconds? Should I go up here or down here? Down here. Watch 60 seconds, 1 minute. Right? Now, what's the theory of why this works and why is it arranged that way? Right? Well, this is kind of like a fraction, 60 seconds or 1 minute over 60 seconds. But wait a minute, 1 minute is equivalent to 60 seconds. So if you, what is anything divided by itself? What is that always equal to? 1. So isn't it kind of like we're taking our original value and just multiplying by 1, which isn't really changing it, but it is swapping out the unit. Because look at this. Seconds cancels, and now this is an equivalent number of minutes, right? Yeah. Okay, so you guys remember this, right? It's been a long summer. Hopefully you did know that, but in case you're a little rusty. Right. So next step would be what divided by what? 1 hour over 60 minutes, right? And it's the same story, right? That is a fraction that's equal to 1, so we're not actually changing anything. But the minutes, now we would have an equivalent number of hours, right? And the last step is 1 day, 24 hours. Hours goes away. Aha. Right. Then pick up a calculator and I'm going to multiply across the top, right? And then divide everything down here, like giant denominator. So 10 to the power of 6 divided by. Okay. I'm going to do it this way. I'm going to open up a parenthesis and just multiply all the stuff down here. So 60 by 24. It's all in the denominator. Yeah, there you go. 11.57 days. And so about a week and a half. Next question. How many years in 1 billion seconds? You sort of had a head start already, right? Or never mind. Start from a billion and then do a similar pattern. How long is a billion seconds? Pause this recording. Recording is resumed, and Alex says 31 years. Let's see if Alex is right. Get some railroad tracks going. High stakes for Alex. Don't find out. So 1 billion, isn't that like 10 to the power 9? Go ahead and do the right? Seconds. I guess I could just copy paste this part of the story here, right? You guys know 60 seconds, 1 minute, 60 minutes, 1 hour, 24 hours, 1 day. Right? Now all the units at this point can't give you days. Then I could say probably about 365 days in 1 year. I guess if you wanted to get more precise on that, but 365, that'll work, right? So let's go 10 to the power 9, then divide by open parenthesis, all these numbers, 60, 60, 24, 365. Ah, that is indeed 31.7 years. Now that's a crazy time scale difference, isn't it? Million seconds, about a week and a half, a billion seconds. Ooh, 31 years.
Trillion.
Ooh, yeah, you do that if you want, but it's gonna outlast any less. How about this? Let's go. How many miles is equal to 1,000,000 inches? How many miles is 1,000,000 inches? That's the answer. Yeah. Let's go, Jackson.
15.78.
Ah, Jackson nailed it. 15.78 miles. So let's go through this. Now this is you'll almost never hear me talk about inches in this class, but I'm just using this as a good conversion example, right? Because you have to memorize all these weird conversion units, they're kind of like pre-metric days. So there are 12 inches and 1 foot, 5,280 feet and 1 mile. Oh, actually, that's the entire thing, isn't it? Because inches, feet, feet. Right. All right. So I pick up. So 1,000,000 inches, 26 inches, divided by 12 times 5,280 all together. Yep, that is 15.78 miles. Okay. I guess if you're allowed to know 4 digits of precision, if not, say 15.8 or even 16. Yeah. All right, good. It was exactly that number. All right. Ooh, let's do a. Let's switch back and forth between U.S. customary and metric. So suppose you drive up to Canada and you see a speed limit sign. That speed limit sign says 80 kilometers per hour. And you want to know, I wonder how many miles per hour that is. All right, let me pause this and get this phone call. Oh, you guys are working on that? All right, resume. All right, recording is resumed. See, Connor said 49.7 kilometers per hour. Let's see. So railroad tracks. So 80 kilometers per hour, right? Okay. Now, miles per hour, a lot of times written like this, but really it's mph is really just a fraction, right? Miles per hour, like that. Okay, so kilometers per hour. Actually, Connor, what did you do for the next step?
To be honest, I didn't know how to actually convert it. So
Okay.
I
Okay.
I will the step 2.
Yeah, so this could be longer or shorter. So it's a short day. I'll just cut to the conversion I happen to know, which is there are 1.61 kilometers in a mile. 1.61 kilometers is equivalent to 1 mile, or pretty close to it, around a little bit. I guess you could, if you want to get it exactly, there is a definition switchover, which is 2.54 centimeters is defined as exactly 1 inch. Okay, so really even U.S. customary units are technically tied to the metric system through that conversion. 2.5 centimeters equal to 1 inch. Okay, but it kind of works out to this. Kilometers. Okay, so really, if you, and this is like a fast way to do it. Okay. 80 over 1.61. So yeah, that's about 49.7 miles per hour. Okay, so which is about 50, right? Maybe that's really what I should say. About 50 mph. Right. So if you're up in Canada driving around, you see 80 kilometers an hour, you know, that's actually 50 miles an hour. Okay. let's solve a pizza party problem. We're gonna have a pizza party. We're gonna have some friends over. I've got 14, let's say 14 people all together. Take yourself and 13 friends. And you're gonna plan a pizza party. Do you think, oh, yeah, thank you. Do you think you might want to know, have an estimate of how many slices per person? Let's call it 4 slices per person. Okay. Let's say that there are 8 slices of pizza per pizza. You guys see like some fractions going on, right? Okay. And you got to figure out, I wonder how much I have to budget per pizza. So there's one more piece of info you need to answer that question. How much do I have to budget? And what's the last piece of info you need? Price of a pizza. And so I'm gonna throw a number in here. I'm just gonna copy the number on my notes. Let's say $9 per pizza. I guess this dollars is like a unit, right? $9 per pizza. I should have written that out, $9 per pizza. All right, so you guys figure out how much do you have to budget for this party? Wait, how much? $63. Oh yeah, $63. So start with the 14 people. Notice that these 3 values down here are ratios, right? Okay, so I'm going to start with like a given value, right? 14 people or persons. Okay. And then go through all these translation factors, and at the end, I should get like some dollar amount. So say I do see 4 slices per person, so I can go like 4 slices per 1 person. Okay. I see 8 slices per pizza. Does the 8 go on top or on the bottom? Where does the 8 go? On the bottom. Yeah, 8 slices for every 1 pizza. Right? Slices. That's up. Okay. And then $9 per pizza. Where does the 9 go? Top or bottom? Not yeah, top. Right, so it's 9. The unit is dollars. And then per pizza. Okay. Pizza's canceled. People cancel back here. You guys see how the only unit left on the board is dollars? Okay. So then I'm gonna multiply across 14 by 4 by 9, and then divide by this 8 down here. That's indeed $63. There you go. Sure, pizza party budget. Ooh, a good application of this. This would be kind of a short one. Suppose you drive 290 miles, okay, and these numbers are a little bit old, so let's pretend it's back in the day, and you spend $19.91 filling the gas tank, and gasoline costs a good old $2.91 per gallon. What is the fuel efficiency of your car? Fuel efficiency. Yeah, Elijah.
Would it be 42 miles per gallon?
Ooh, I got something a little different, although that is the right order of magnitude. That is a reasonable number. Unless I wrote something wrong. I think it might be.
$42.3857.
Yeah, what you got?
30.69 miles.
That looks really close to what I got. I wonder if I have a typo. Let's see. Okay. So this one's a little different than the other ones so far. I might technically run through a formula than a straight conversion. Because see what I'm asking for fuel efficiency. is not really any of these numbers, so this doesn't really strictly follow like a strict conversion. Okay? But this is actually getting close to that story that I just promised you guys a minute ago, which is you have to think, well, what is the unit for fuel efficiency? And you guys have actually been telling me that, right? You guys say, well, it's miles per gallon. So hey, I wonder if we could somehow rearrange these numbers in these units so that they line up and give you miles per gallon. Well, I do see that miles would be in the numerator, so I better take this 290 miles and put it up here, right? 290 miles. Okay. Oh, technical detail. How this actually works is you fill up your gas tank to the top, then you drive around for 290 miles, then you go back and fill it to the top again, okay, and then all this can work out. Okay, and I also want gallons to be on the bottom. And so this $291 per gallon, I could write it like this, right? $2.91 per gallon. That gives me, okay, so now you guys see how these units are clicked in place? Miles to click, gallons to click. Those are exactly in place where they need to be. But I've still got the dollars in the way. Oh, yes, dude. Aha. Exactly. If you tag the $19.91 down here, the dollars cancels out and it leaves you with exactly the unit that you're looking for. All right, good call. So let's try this out. It's 290 times 2.91 over 19.91. I need to change these numbers. It's like the same 3 digits over and over. I'm getting, oh, hold on a minute. Did I type something wrong?
I did something wrong.
2. Oh. Okay, yeah, I had to dyscalculate a moment. So actually, yeah, Elijah had it right the whole time. Okay, that is, I wrote the number differently than in my notes, but we'll just go with this because this is what I have written right in front of us. That is indeed 42, 0.38 something miles per gallon. Okay, yeah, you guys were right. I just copied my notes wrong. All right, there you go, miles per gallon. All right. Let's do. All right, so sort of story attached to this is back when I was at college, I got my undergrad degree in civil engineering, and before we graduated, we had to take this really hard exam called the Fundamentals of Engineering that covered a bunch of engineering classes that we had been through, but also it involved a bunch of topics and classes that each of us individually had never been exposed to or taken, right? So we're seeing these terms and variables that I've never been in a class that would have involved this. But fortunately for me, that exam was multiple choice. And so if you looked at all the numbers and attached units, I just used one trick over and over and over on the exam. Again, it was just this dimensional analysis. Well, to get to the answer that would answer the question, like, well, you'd have to like slide these variables so the units will like click in place like this, and then okay, well, hey, there's a multiple choice answer that does that. Now, what you would be missing from that is if there was a formula that had like a 1/2 factor, possibly like, oh, it's like, for example, kinetic energy is 1/2 mv squared, right? So you can't really get that coefficient if it's just numbered, but you can get the units in place where everything clicks in place, and then that got me through that exam. All right, let's do this fun example. Let's say you have 1 ton of pennies. You know what? I'm gonna come back to that one just because we got about 11 minutes of class. There's a couple of other problems I really wanted to hit. Actually, yeah. Let's do this. Okay. Force. We're gonna do something a little bit different. Force is measured. Force is measured in newtons, where 1 Newton is equal to 1 kilogram meter per second squared. Okay. Did you guys possibly in a prior science class learn a formula called F equals ma? Okay, force equals mass times acceleration. So if there is a mass and you push on it with some force, that causes it to accelerate, right? Look at this. Force, Newton, is mass kilogram and meters per second. Meters per second squared is like a rate change of velocity, right? So that's like next week's stuff we're about to get into. Okay. Wait, where did this go? So we got speed measured in meters per second. And let's say a radial size r measured in, you could say meters, meters, centimeters, some version of that. Okay, so we got newtons, meters per second, meters. Guess that. Okay. Oh, and oh, I'm missing one. Oh, okay. Mass measured in kilograms. Okay. All right. So with that established, suppose there was here's one of the labs we're gonna have you guys do one day. Right, is you guys gonna take a mass, you're gonna wheel it around in basically a 4-tunnel circle, so it'll be a little bit simplified, and it'll be attached to a string. The string is going to be looped through like a PVC pipe, and there's going to be a weight down here, providing like some force. Okay. Hey, do you guys see the tension in the string? Tension. Hey, remember the hungry monkeys pulling on the bananas? So tension is a kind of force, right? That you can measure in newtons. Okay. Would you think the tension of the string would match this weight pulling down if this weight, bottom weight, was in equilibrium, just kind of hovering there? Okay. So here's what we got. I'm going to match these variables to this picture. This radial size here, I'll call r, that you can measure in like some number of meters, right? It's like 0.45 meters, right? There's this mass that's swinging around. I'll call this m for mass. Okay, and if you know how far it goes, like the circumference of that circle, and you time it, could you go distance divided by time and get the instantaneous speed of this thing? Call that lowercase v. V velocity, like a speed, right? And it would be speed, about magnitude. Or I guess if you're super tricky, you got this. You just wait through this thing. Oh, that'd be really hard to do. But okay. I want you guys to tell me. Oh, and then this thing has a weight, which is pulling straight down with some force, which is also providing the tension. So like, what is the tension force that's holding this top mass in a circle? Do you think the faster you wheel it around, the more the tension force is required to keep it in a circle? You guys can see that, right? You ever like wheel a ball around in a circle? Faster you go, you feel that tension force build up. I want you guys to tell me, what is that tension force, the force equals, in terms of these other 3 variables. Give you guys a hint. I'll give you guys 2 hints. It's a fraction, and also one of those variables might be squared. Okay, now this one takes some thinking, so go for it. It's a fraction, one of those variables might be squared. Who's going to get this? So I'm looking for a formula, right? Things multiplied, things divided, somebody's going to be squared. Anybody think they might know? Yeah, what are you thinking?
R over M times E.
Okay. Okay. So let's try it. So we got one idea on the board. R over M times V. Okay. Let's see how the units would play out. Let's see if these units would match and ultimately give you newtons, but or not. Okay. So radius would be measured in meters. Okay. So I'm going to do M for meters. So this is a unit. This M is a variable, but it's different things, right? Speaking of the variable M, that's in kilograms. So I put kilograms down here. And then V would be in meters per second. So that would give you meters squared per second, and then divided by kilograms down here. Does that look like that? Not really, right? Oh yeah, what you thinking?
M over R squared.
Rick got it. Yeah, it is mv squared over r. That'll do it. Right. So let's check the units. I want you guys to see that when the units settle, when you plug in the units and everything settles, it looks exactly like this, which would represent newtons, which is a force. Okay. So this m mass, that could be in some number of kilograms. this V is in meters per second and it's being squared, right? So wouldn't that be like, yeah, meters squared over second squared? Because this part is this V squared, right? Okay, then it's all divided by radial size. So extend this fraction, divide by radius, which should be in meters, right? Meters per radius. Okay. Let's see. So V is meters per second. If you square that, it gives you meters squared per second squared. Right here, meters.
Oh, no, I got it.
Okay, yeah, you got it. Yeah, so just in case anybody else was wondering, that's equal to that, right? You guys get that? Okay, yeah, so let's skip a little stuff there. Do you guys see one of the meters is gonna cancel? That leaves you with kilogram meters per second squared, which is 1 Newton, which measures force. Got it. You guys see that? Okay. Now, if you're constructing this from scratch, the one thing you wouldn't know exactly just from dimensional analysis, like, is there like a 1/2 factor? It's like, well, maybe. It turns out there isn't. This is actually a V formula, but just looking at units, the best you could say is like this is proportional to that or something. Okay, but it does turn out to be equals. Okay. All right, so that'll be a feature of that. I'm going to leave you guys off with a challenge problem. Ooh, maybe this could be a good weekend problem. Okay, so here we go. We got the USA energy usage is 25,000 terawatt hours per year. 25,000 terawatt hours per year. Okay. I'll tell you guys that tera equals 10 to the power of 12. Right, that's this guy right here. That's the prefix. I'll tell you guys that the average solar flux is 400 watts per square meter. The maximum solar flux is 1360 watts per square meter. So, 12 o'clock noon, bright sunny day, 1360. But if it's like, sometimes cloudy, sometimes it's nighttime, average 400. And I'll tell you guys, 1 kilometer is equal to 1,000 meters. And let's suppose, that the efficiency of solar panels equals 20%, right, which is like 0.20 as a decimal. Okay, so challenge problem. See if you guys can figure this out over the weekend. If you want a good challenge, right, is how much land area to supply energy demand. Now, this is what's called a back of envelope calculation that you guys are going to do to solve this. Obviously, we're skipping a bunch of engineering complications and intermittency and battery storage and the whole thing, right? But let's suppose you were to get all this energy supplied just from solar panels. How much land area would that take? And you can solve that with those given values and dimensional analysis. All right, you guys have a great weekend, and Monday we will have a super expensive lab rolling Hot Wheels cars. Yeah, okay, all right, I'll see you guys on Monday.